Are we all on? Can we start? Yes, okay. So the idea is to do, high precision. I'll talk about this, I think it's tomorrow, the colloquium, no? Yeah. Maybe I should have had the colloquium first. High precision gravitational wave science. And what we've been working on is some modern approaches. To the relativistic two-body problem. So, because I've done both, in my first lecture, I'm going to set the stage to what the modern approaches are. So mostly what I'm going to talk about here is setting up this two-body problem, and then ultimately we're going to get into the modern part. See? But the main goal, I have colors, is to do gravitational wave science. Of course, the tools and learning about how to solve the two-body problem in general relativity and gravity is fun, right? But we have data now. We have gravitational wave observations. So ultimately, what we want is to learn about these guys. So we have two guys, and I'm just going to do this diagram now so we can set up the problem. That they go around. They meet gravitational waves, and we're here, and we see them with the interferometer. And what's the goal? Well, there's a lot of traveling, right? So I'm not going to talk much about this part. We can learn a lot about the propagation. We can learn a lot about cosmology by looking at how far these guys are. We can do standard sirens. You had maybe last week you had a whole thing about cosmology, no? Ricardo, wasn't it also cosmology with gravitational waves last week? Mostly astrophysics? Okay. There's a lot of physics we can do. But what are we, or what am I mostly interested in, is to learn what these things are. So these are some compact objects. Now, how they formed, how they get to form pairs and emit gravitational waves is part of the whole deal. There is a rate for these events that we're going to learn about. There is a frequency band in which we can detect certain type of objects between maybe a few solar masses to maybe 100 with what we have right now. We're going to have a next generation with the Einstein telescope, with the LISA in the sky that will see very heavy guys. And by the way, why I insist on these compact objects and I don't say black holes or neutron stars, if you recall, and maybe I'll say that in the colloquium again, but the Nobel Prize for the people who discovered that there is a big object in the center of the galaxy, right? If you read the prize, that one also went to Roger Penrose. It does not say because of the discovery of a black hole. It says the discovery of a supermassive compact object. We still don't know what that is, right? And that gives us the chance to actually learn about these guys through gravitational wave observations and really determine whether those are the black holes of GR or not, right? Probably I mentioned this again, but Roger Penrose was the first ever person to get a Nobel Prize for something that might have nothing to do with nature, right? Because we still don't know if general relativity is the correct theory. We did not yet prove that, right? We all believe it is. I believe it is. There are no alternatives, right? That's another story. By getting the prize for the formation, the inevitability of black hole formation in general relativity, and then say, well, we discovered that we still don't know whether it's a black hole or not, the jury is up for grabs. So that's what I want. I want to learn about these things. And here comes the high precision part of the story. Why? Because to really look at here, the waveforms, for example, We look at some waveform far away that we're going to observe through the LIGO detector because that's the thing that stretches the length and so on. This depends on the structure of these objects. But how the structure enters in the waveforms is a very high level of precision in the solution of this problem. In particular, as I will sketch in a minute, if you want to learn about the UV scale of the theory, I'm talking about in QFT languages, and now you see how the modern aspect of the story starts. There will be a lot of quantum field theory language and calculations that would be based on quantum field theory and scattering amplitudes ideas in the more modern approach. Is that what is the UV physics of the theory? This is our UV. The high energy physics of the problem is what's happening inside the subjects. And if you want to learn how this scale R enters in the waveform, you have to go through this scale, which is the motion, and then through these scales, which is the emission. And there is a very nice separation of scales here. And therefore, when we measure, say, a phase, the gravitational wave phase, that enters here, it has a phase. There will be entering this scale R in the phase, maybe based on the solution of Einstein's equations to some power. Because it's gravity, if these were points, I can never tell, right? If I'm in the elevator, I'm free falling, I don't feel anything. How do I know that gravity is there? Gravity is there because I'm falling here, this falls there, but we don't fall exactly the same. Exactly. These two geodesics are closing each other. There's a deviation. But that caused me curvature. So this point and this point, say, on the surface of this planet, they don't exactly fall the same way in the field produced by the companion. But to feel that deviation, it costs me two derivatives of, say, some potential, if you have some potential interaction. So you start seeing that it costs me derivatives. Now, derivatives of the potential are the forces. And the forces are determined by the binding energy, which is Gm over R, which in a bound state go like V squared. So you see that just seeing the deviation of an object that just has a size will cost me two derivatives of something that's already starting to scale with powers of V. So how are we going to see it? We're going to see it because this guy is going to deform. This is going to start pushing. These guys are going to press, and it's going to get a quadruple. If it's originally spherically symmetric, it gets squashed, and it gets a quadruple. So it costs me curvature just to squash it, and that induced quadruple, if I look at how it couples in the theory, as we will see, it will also couple to two derivatives of the potential. In fact, here there is some fancy words that actually couples to curvature, and we will see that what matters from the curvature is when you remove the traces, because all the traces of the curvature are zero everywhere. The R mu nu is zero, and the R is zero. Those are Einstein's equations. So everywhere, Einstein's solution. So the true curvature is when you take away all the parts that vanish. So the Riemann tensor without the traces. That's what replaces this. But Newtonian-wise, this is just a very easy coupling. This is what generalizes in electrodynamics, the standard P dot E. Now, the P could be, a dipole could be induced by some external field. And then you have the susceptibility. So you have an induced P that is proportional to some external electric field. So the coupling in the action will go like E squared, because the induced guy will go like E, and it couples with an extra E. The same is going to happen here. And then you see we're going to have a lot of curvature couplings, and that's why the structure, at the end of the day, first enters a fifth what is called post-Newtonian order of order v to the 10. Actually, I'm cheating a little bit, as you'll see in a second. Because here, I'm essentially counting the size of the object, r, as if it goes like the order of gm, which is the length scale of the problem. So there's a natural length scale in the problem if these guys have mass m, which is of the order of gm, which relative to the distance is v squared. But here, there is an extra parameter that I'm ignoring, which is in here, there's an r over gm parameter, because what really matters is essentially how the scale r enters relative to the typical scale, which is gm over r squared, which is v squared, but the uv scale is r. So here, what we're going to get is not gm, I say it's comparable, but we're going to get is r. There will be r to some power. So if I put gm over gm, I get the gm over r, so v squared, but there will be a leftover r over gm to some power that can enter here and enhance this effect. For a black hole, we think that r is order gm, so this will be order 1. So when do we see the structure, which is how the black hole reacts to the presence of a companion? We will see it around the 5th post-Newtonian order. This is just power counting. I don't have to do anything. For a neutron star, say, the r could be a few kilometers above, right? So maybe 10 kilometers for a solar mass. And therefore, this is 2, this is 10, this is 5. It turns out to go to the 4th power. So this could be a large number. And why is it a 4th power? It's because the quadrupole is mass length squared. There's another length squared, so it's mass length to the 4. And length to the 4 is what you want here. This sometimes go by the name of love number, which is this proportionality between this analogy in gravity with the quadrupole and the curvature is called the love number, and it scales with this 4th power. And why do I tell you all of this? Because this is the only thing we care about. This is the scale at which we want to see the structure that will tell us whether this is a black hole or a neutron star, or something else entirely. Of course, you're going to tell me, no, but wait a second. There is a dipole too, sort of, right? These guys could be spinning. And then the spin could induce a quadrupole that is not a response, but it's just intrinsic. If this guy is rotating, he has an intrinsic quadrupole. You can measure that. And it's true. But the spin first could be small. First, you need to know the exact parameters, the value of the spin. It's a little bit more complicated. This is very clean. If the spins are small, you measure these guys, and then you know that there is a relation between this structure and what these guys are. And now comes the fun part, and this is mostly my motivation part of the discussion. As Nathan runs away. It is that the love number, which measures this response, that, I mean, probably many of you already know about this, right? If you don't, please ask questions. The love number, that response function, the induced quadrupole moment to an external perturbation, this is just the E associated with curvature the same way that this E is associated with electric field. This is called the love number. It's 0 for Einstein's black holes in 4 dimensions. And it's not 0 for neutron stars. In fact, well, it depends. If you do the dimensionless version, which is divided by these GMs, the dimensional inversions of this love number could be up to 1,000. So times a v to the 10, that could be 0.1 near merger. I mean, you have a chance to see it. And in fact, people do use this enhancement of a large love number to actually get towards the end of the evolution of the phase some idea what the size of this departure from this point particle approximation, in which we see size, whether there is a deviation in the data that points towards a structure. For neutron stars, there is some indication that there is structure, And that's what we want. Because if we know it, and we have a way to say how rigid the star is, or how big the star is, then we learn about the structure. And if you see something that has structure, and is heavier than a neutron star, then we discover something that is not there in nature. Or that is there in nature, but it's not there in our stock of theories. Because if we have a love number, it's heavier than a neutron star, and it's not Einstein's black holes. And there is nothing more motivational than this. We really don't know what those guys are. And by measuring through high precision waveforms, what the structure is doing up to very high order in the evolution of the phase, we can learn about neutron stars and maybe new states of matter, whatever, but even the black holes of general relativity, whether those are the ones that are producing the gravitational waves or not. So that's essentially the main motivation for this, or for me at least, is because if you really control your waveforms to very high level of precision, then you know for a fact whether you can see deviations in which you might find something that is unaccounted for. And what you can find, well, that's another story. What can produce this, which is not Einstein's gravity? It could be Einstein's gravity, but I'm just going to mention this briefly. One thing that can happen is that you could have the black holes of GR, but they could have some environmental effects. There could be something around them. And one of those somethings could be dark matter. And one of those something dark matter would be axion-like particles. Now, obviously, if you have black holes of this scale, the axion-like particles that you need are very light. So they could be, for example, between 10 to the minus 10 and 10 to the minus 12 EVs, right? So it's very ultra-light dark matter axion-like particles. They could condensate around the black holes, and those could deform. And if they deform, they produce a love number. If they produce a love number, I see it in the data. There could be a boson star. There could be something here which is made out of completely new particles themselves. Of course, they cannot be free. They have to interact, so it's not just gravity. And it's counterintuitive, right? Because the interaction, what it's doing is preventing the collapse. It has to push out, right? It's not that you want to form the star by pushing in. You want to keep it from collapsing. So then you need a self-interaction that pushes the pressures out, right? Which is what the neutron stars do, by the way. Basic knowledge of physics, right? A neutron star, which is about 10 kilometers, there's a Fermi size of the neutron, right? You put 10 to the 20 or 10 to the 30, whatever many neutrons together in the Compton wavelength, and you do a Bose-Einstein condensate, you don't get to 10 kilometers, not even close. The reason you get to 10 kilometers is because they are not bosons, they are fermions. And you cannot put them all together. And that's how quantum mechanics gives you a star in the sky, right? This Pauli. You turn off H bar and bye-bye star, right? So boson stars cannot exist because the exact same reason. You need something that does the job of the Pauli pressure. And that's why you have to cook up some modeling which you keep the star together, stable, at least for sufficiently long times. Very good. So all this is motivation. But there is a lot of motivation. There's also the motivation, which I'm not going to discuss much about. By the way, when I say that if these are the black holes of GR or not, I'm saying that it could be the gravitational interactions. It could be all this dark matter, all this, but it could be the gravitational interactions themselves on scales of the kilometer could be very different, forming objects completely different, right? As much as, I don't believe this particularly, but there are models in which as much as the neutron star is kept together by quantum pressure, a black hole itself could be some kind of fast pole type of thing, right? And those we can also tell by measuring to high precision these waveforms. Yeah? There are solutions inspired by string theory in which the geometry might not have a singularity, an horizon singularity. It might be different, must be very different solutions than the standard GR solutions. And those, in principle, might have love numbers which are not 0. We don't know what's out there. That's the whole point. Even before we started discovering anything, if you tell an 1800 physicist about black holes, they say, you're crazy, right? Well, we don't know what's there, right? So, but I'm talking always about this UV physics, right? So I'm saying there could be on very short scale, which are order kilometers, modifications on scales like the neutron star, in which GR can have maybe large quantum effects on horizon scales that could also be relevant. So that's also motivationally horizon physics that can change what these objects are. But then comes another part, which I'm not going to talk about because I don't like it. But this is my bias, and you don't have to follow my bias. Which is when I wrote this, I'm saying, here it holds, here is Einstein. And I'm not going to touch it. I don't know what's happening in here. And the reason is that whatever happens in here, I can still model in my system as some structure on short scales. Because I'm going to calculate mostly here, and I'm going to treat this as some unknown UV physics that's going to address my theory. But here, the long distance still GR. I'm not going to touch that one. I don't want to touch that one. Yeah? But you can touch that one. So there could be long distance modification of gravity. I'm not going to touch those. Short distance modification of gravity, I'm fine. Because the states that gravity could form, I still don't know what they could be. Right? Very good. So that's essentially the motivation. And because we come with all this modern approach, if you want, about quantum field theory, and I mentioned here UV physics, well, the idea will be to treat one of these scales at the time and match into descriptions which are valid at different scales. I want a description which is valid on the scale R. I want a description that is valid between two objects at the scale little r, and then another one at the scale lambda. At each step, there will be some infrared physics to this UV. There will be some infrared physics to this UV. And that's the catch of how to construct these theories. So the main idea will be to say, okay, there is a scale R that I don't control, but I integrate it out. Because I'm going to have two of those guys. And therefore, the probe of the scale R is much longer than the size of the UV scale. So if you want, from the point of view of the companion, I can see this guy as a point-like object with some structure. Yeah?
There was a question about the order of magnitude of log numbers, for example.
Do we ask questions? I would like to know the order of those log. Good question. Yeah, for a Boson star, some people have done some of these calculations. So for a Boson star, what I've seen is mostly a little smaller than neutron stars, maybe order of 100, the dimensionless divided by GM. For these guys, this we did. We were the first to, I mean, this is known since a while, but we were the first to actually study the binary case of these axion-like particles. And actually, with a student of Daniel Baumann, while we were here at the ICTP in a school, we started looking at this. This could be humongous. In fact, the log number of the axion-like particles, which are sometimes called the gravitational atoms, those could be 10 to the 5, 10 to the 6. They could be very, very large. And the reason is because it's like QED. The size of the nuclei that determines, in the case of an atom, right, in electromagnetism, has the Bohr radius, which is enhanced by alpha, right? And alpha is the coupling. And it's the 1/37. So that's why the atom is mostly empty. There's a lot of space until you hit the first state. The same happens with these guys. There's a parameter alpha that plays the role of the QED coupling. And that parameter alpha says that the radius, the size, goes like 1/alpha squared. So it's Schwarzschild radius divided by 1/alpha squared. And that makes, when you do the to the 4 to get these guys, it gets a very large number. And that's why these love numbers for the axial light particles could be very large. The same way that the atoms are mostly empty. The wave function of these guys look a lot like atoms. And therefore, that's a very good question. Therefore, you can, in principle, through tidal effects, see the fact that the black hole is stressed by this axial light particle. I can mention some of that later if you're interested. How can you see them? Very good. Yes? How do you do the match? You have to ask Ricardo. I mean, it's not obvious that you get some waveform, how you go and fit the data, right? The data analysis is a little more complicated. How people take into account the fact that you do or you do not have love numbers depends on biases. For example, if you know it's a neutron star, you set the mass. Don't let it run. Or you say it's low spin or high spin. So it's non-trivial to really discriminate these things, right? So that's a little bit of how you construct templates. Of course you can. Yes. Originally, I think, okay, but you were not going to ask that. So the question is not what I thought was the question. So what was the question again then? Because I answered a question that wasn't the question.
Okay, my question is, if you have a given waveform experimentally measured, is there more than one possibility for the internal structure of the binary?
Absolutely, it's just one number. I just told you about one number. Maybe if you go higher, you get more numbers. But, I mean, there are many theories that will fit the number. Supposedly, if you believe in Einstein's gravity as the true description of nature, if that number is not 0, then you learn something. It's not this kind of theory. But what theory it is, could have the boson star, could have love numbers which are 100. If you see a number which is roughly 100, could be a neutron star, or could be a boson star. How can you distinguish? Well, the boson stars are heavier. The neutron stars are a few solar masses, the boson stars usually heavier. So that's how you distinguish. You distinguish because you measure the spins, you measure the masses, you measure the love number, you measure whatever comes next, and then you measure, for example, how the spins are oriented relative to the plane. So there are different combinations on the spin. You measure the internal quadrupole moment of the object that depends on the spin. You put all that in structure. The point is that the structure will start to peel off at different orders. When you see, maybe we can talk about that, but it will take me a little bit. You start seeing the waveform. Then the first thing you see is the chirp mass, right? It's the first order thing, if you know what I'm talking about, right? That's a combination of the masses. You cannot tell them apart. You don't know what M1 and M2 are. So then you start going to one post-Newtonian correction. So the first V correction, which is when you start getting closer, is more relevant. So as the frequency increases, you get the mass ratio. So it starts to peeling off from the waveform, chirp, mass ratio. I don't want to write and then erase it. See? Then you come the spin orbit coupling. But it comes in a combination. There's like a chirp spin type of thing. Then the 2pn comes, the 1.5. The 2pn comes the spin, another combination. Then you keep going, and you start disentangling everything. For example, the love number does not come alone. It comes in a combination of 1 plus 2. So you need to disentangle that one too. What you can do is that you assume, for example, they are very similar. So you say there is a bias in those two neutron stars to have comparable love numbers and so on. So how this works is another story entirely, right? My whole point here is conceptual. There is a theory of gravity that we're going to say is Einstein gravity on long scales. I'm not going to change that. It's mu equals 0 everywhere outside. Period. Done. That's easier said than done, obviously, right? Solving these equations is extremely hard. But I'm going to assume that those are the equations. Now, where is all the information about new physics? Inside these guys and in structure. And I'm going to tell you how am I going to parameterize that structure by integrating it out, because it's UV physics for my IR waveform. And that would be the catch. That's what the effective field theories do. I go to the standard model of particle physics, and I have the standard model that describes all the particles that we know. I do a scattering calculation, right? And if I want to know that there are no new heavy states, but I did not produce them yet, I match into some effective theory of the light states, in which I integrate out the heavy states. So you have two light guys, some heavy guy, some light guys, and then I say, this is like in some effective description with a new coupling, right, that we suppress, for example, not in this case, it would be the W, say, by some heavy guy. No, in this case, just the coupling, and then the derivatives will be suppressed by heavy guys. That's G Fermi, right? So it's the same thing I'm going to do here. My life states is because I don't get to see those scales, right? I'm observing the waves that come out. But I know the effects of the short scales on the waves that come out. And I want to parameterize to read off what that is. Inverse G Fermi gives you a scale. That's why we built the LHC, right? Well, the LHC, it was also understanding why scattering, unitarized scattering, and so on. But there was a scale that told us something about electroweak. Here, our scale is a little more difficult because the ratio of these parameters, I mean, there are scales, GM, right? But GM is a length. So the scale for R turns out into some order of scale, right? So rather than saying I had to get to 1 TeV, I want to get to 5 PN. It's where this manifests itself in principle. But indirectly in this case, it's not that I'm producing the states as I will be doing with the LHC, right? But here is when this first operator, if you want, in this higher derivative expansion of an effective action starts to manifest itself. Because I see effects that are suppressed, and if the power is high, and I want to measure a cross-section, I want to get to a level of precision in which I control this order of error, right? Very good. So that's our goal. We're going to integrate out this scale R, and we're going to construct an effective theory the same way that we do with the light and heavy states. My life states are all the gravitational degrees of freedom outside. It's a theory of gravity. So I'm going to match into a wall line. So this is a 3+1 dimensional object. I'm going to go into a 0+1 dimensional object. I'm going to get rid of the scalar. If I get rid of the scalar, then it becomes a point. And therefore, this object, which in principle is described by the motion, say, of the center of mass and the rotation of the center of mass, it will become some center of mass coordinate. I'm not going to put center of mass, but it's some generalized coordinate that will tell us what that object is. And even though that sounds trivial, it's actually not. And I'll tell you why it's not in a second. And then there is some frame, say, that rotates, that describes the spin of the object. If you want, sometimes I call it I. This is 1, 2, 3, 4, or 0, 1, 2, 3. And this is the guys that determine the metric, J. Well, in this case, this is eta J. I mean, I'm just doing the, I mean, the locally, these are the guys relative to the frame. Shall I call them differently? These are the guys that determine the metric, or equal, G mu nu. And these are the guys that rotate with respect to these guys. This A frame, this A index is the with respect to this frame. So sometimes these guys are called like a boost. because there is a frame, E A mu or A mu A, whatever I call it, A mu. In every point, I can go to a free-fall frame where it's a Minkowski, right? And in that frame, the rotation is a boost. Well, it's a boost or a rotation, right? So I have those degrees of freedom, right? And there is some omega dot omega rotation matrix that determines the spin. I'm very sketchy because I'm not going to have time about a spin that could take me into a completely new territory. That was my PhD thesis. Obviously, I love spin. We're going to have a talk by Fabian on spin. But just spin itself could take a while. So I'm not going to talk much about spin, but we have to include it. We have to include it because, in principle, if you think about symmetries, the black hole, so you start with Einstein gravity, right? And then you solve these equations, and then you find black hole solutions. So the black hole is somewhere, and it's rotating somehow. So you broke translations and rotations. So you have the light degrees of freedoms associated with breaking translations and rotations, and that's this field is the light field, which is the collective motion of the center of mass, and this field, which is the collective rotation. If I use fancy words, that's sometimes called the coset construction, just to be fancy. I don't really like it, to be honest. I like the freaking frames. But there's a way to study the symmetry breaking pattern or which symmetries you break to construct these cosets, to construct the action as well. And that's why I said at the beginning, why? This is non-trivial, because you have to make a choice. And if you think, for example, that you take an object, and this is a footnote. You say you have an object, and you have an object that rotates. So it rotates about what? And then you have an object that has a center of mass, and you say, okay, I'm going to choose the center of mass, define the center of mass, right? What do you mean? Okay, let's say we have a definition, center of mass, or center of momentum, or center of energy, and we rotate about that center. But if I'm here, obviously, I have a shift, and then my rotation is different. That is because we have too many degrees of freedom here. If you have a spin, which is what you do when you have this rotational matrix, and you contract the indices, so you have two open indices, so AB. This is like a spin, right? So you end up with some spin, which is the conjugate to this. And this is antisymmetric, and it's 4 by 4, so it's mu nu, right? Space-time. So you have 6, and you have 3 too many if you're going to describe rotations. So sometimes what is called, you make a choice that chooses precisely what that guy is, and that's called the spin supplementarity condition. This is literally just a footnote about spin, because there's a lot of discussions right now about what this means, and what this means, and what this means. Ultimately, then Ricardo comes and says, who cares? I measure this, and that's what I care about, and I do the data analysis, I get some parameters. Now you go and tell me which parameter corresponds to what I measure, right? And that's a discussion, because obviously there is a total angular momentum, and these guys are going to contribute to that momentum, right? So you need to extract the observables of your theory. And what describes the intrinsic spin, the total current, the charge associated with rotation, is what matters. Then people are going to say, well, are you really just 3 degrees of freedom? What if you have more? Well, we don't have a dipole, an honest dipole in GR, right? Some people are saying, well, maybe you will do. Maybe this here is something that you can see physics of. We think it's a gauge thing, but because there are no more than 3. But there are some discussions that I'm not going to get into, because maybe if I'm recorded, I shouldn't say much what I think about it. But it's an interesting question. Let's put it that way. So that was all about spin, which in GR spin is non-trivial, highly non-trivial. But it's it was one of the most interesting parameters that we can observe. Why? Because it does tell you a lot about the astrophysics, how these guys formed. whether those guys, well, there are many scenarios. This dynamical capture, say, you have many black holes in globular clusters, and they just find each other. And gravitational waves play a key role, by the way, because as you get close, you emit at the periastron, you lose energy, and eventually you get capture. If you do that, then the distribution of the spins is completely random. Also, you can get eccentric orbits, because even though when you radiate, you lose eccentricity, if you did that a few orbits before, and then you enter the band, then you can still carry some eccentricity. And in fact, there is some indication that maybe one of the events that we have in the data right now, although I'm sure that the LIGO people will tell me that this is rubbish, but maybe it does show some eccentricity. Some people even say it's a scattering event. I don't know. Of some even new states. I mean, some people argue, if I'm not mistaken, that there might be some funny, fussy event. So that's one scenario. But another scenario, which is this common envelope, that this explosion, that, well, first you form one, and then the other material is accreting and forms the other, they tend to align the spins and the angular momentum. So if you see anti-aligned spins, that is funny. Right? So that's why the spin matters for these formation mechanisms. We also showed recently that if you have this cloud, you can also create eccentricity. And what happens with the plane and the inclination, some people have also studied that. And there is some back reaction that could also be an indication that there was some history of some dark matter cloud around it. So again, solving the equations, understanding the dynamics will tell us about what are they and how they form, and maybe about the cosmological history. So for us, it will be to try to then solve the equations, in which we put two of these guys in a binary, and then we try to compute the gravitational waves emitted by them. So spin, as I said, is very important, perhaps the most fun of the parameters, because just measuring the mass before we get to the 5pn, right? Just measuring the mass is kind of boring. This gives you non-planar physics too. In fact, if you just look at the solutions, if you look at the solutions, for example, a small particle around a Kerr black hole, a small spinning particle, they fill up the entire space, right? There are beautiful simulations that you can track, and that's just like around a Kerr solution, right? Imagine comparable masses, right? So in principle, if I'm not mistaken, people even argue that it's chaotic. So spin is fun. We're not going to talk about spin, because otherwise we don't talk about the other fun stuff. So we don't spin. So we are somewhere, and we move in time, some proper time. Sorry, I should maybe use white. By the way, this is just also what you've done in high school, undergraduate, when you study like relativistic mechanics, and then you say you have a point particle, and then you construct an action for a point particle, right? So what action do you write for a point particle? Well, you write md tau. And if you have two particles, you sum over the particles. Where this guy, d tau, is some metric, g mu nu, x dot, lambda, sigma, not to confuse with lambda, some affine parameter. And this is for each particle. And this is located at the position of the particle. We will see that this is good for this problem, but most of the modern stuff will come from mapping scattering into the bound case. For scattering, this is bad. The square root, not good. Why is the square root bad? Or why is good, say, for this and not the other? It's good because the moment I have freedom, I can choose whichever affine parameter I want. And it's very convenient if we are measuring the waves here with some clock here that we can coordinate, if you want, with the clock, the Schwarzschild clock of the binary, say, T, then that's very convenient, because then we get the phase with our clocks, with the standard Schwarzschild clock, if you want, because the binary as a whole, as we can see, can also be mapped into some one object in a minute. So there is some T of that solution. That's the T we want to choose. Also because we're going to find the motion in time, that we're going to get into some evolution of the binding of the system, that then is going to tell us how this phase evolves in time, right? Because we care about time, because we care about frequency, we care about how this phase evolves, so we care about time, we care about choices. Using the proper time sucks, because you're free falling in the field of the other guy, so you have to really take that into account. Why scattering does not have that problem? Because we go to infinity, in which the influence of the companion is gone. And therefore, it's much better to work directly with the action in proper time, which then becomes the so-called, well, according to Thibaut Damour, it's not Polyakov action, even though we call it the Polyakov action. I don't think it was Polyakov the first to introduce this linear action. It's because of the Nambu-Goto action that Polyakov did. This one that becomes linear, well, it depends, and there is the Virvine that we put to linearize it, right? This, then we choose the proper time, and eventually we integrate it, and we get just this in proper time. And the good thing now is that the proper time is bad for the bound case, but for the scattering, in and out proper time, no interaction. And therefore, this is a linear theory, it's much easier to solve. And because we integrate in proper time when we do scattering, we don't measure proper time, we just measure an angle. Then this is much better than this. Here we care about the phase evolution, here we don't care. And that's why sometimes you'll see that this is used. Actually, we started using this one in scattering, even though for PN, we were mostly using this one because of this freedom. Okay? So there are goods and bads. The square root, not so great, but the choice is convenient. You can do this here as well, but then you have to double the amount of work because of the ease, and it's not clear to me that that simplifies your life. But then here comes the first question. The math was inside, sorry. Who is this guy? Say I have an object like this. I construct my effective theory in which I shrink this guy to a point. And then I write this. And then these m's appear. So if I have only one, I would have had just one. And this is the choice of signature. It's 1 minus 1 minus 1, sorry. The eta. That's why the minus. Unlike the relativists that put minus here. So who is this m? Who is the m? It's very suggestive that I call it m, no? Sorry? What is the mass? So it's an object, right? It's this object. So what is the mass of the object? That should be an easy question. I don't know. I don't know. That's the answer, yes. So if I tell you, for example, that this is a neutron star, how do I know the mass of the neutron star? You see that one of the observables that we're getting is how heavy the neutron stars are. So this m will appear here in structure, even though I was saying 5 p.m., the first, yeah, but first of all, you have m. It's right there in your face. The m we're going to observe, how heavy, of course there are theories about how heavy they get, and we can compare those with observations and so on. But this, for us, is an unknown completely. We don't know what it is. We're going to get it out of here, right? And how do we compare this with theory? Well, we do a matching. We say, well, I have a full theory. I know what the UV is. I'm going to go in the limit in which the probe is long, and I'm going to read off that parameter. Or if you know how to calculate, if you're strong enough, you can actually compute it. Like we will do, by the way, when we do the binary, we will do that explicitly. The binary itself is going to look like this. When we look at width far away, from the point of view of the radiation, the whole binary is going to be a point, and it's also going to have an M. And this one we can calculate, because we know the full theory. It's going to be this theory. Now, the question here is, who is M? So if I have a neutron star, I have a bunch of particles. Is M equal, question mark, the sum of the particles? Is the M the same as the sum? No, it's not. Why? Because if it was, they will just fly away.
Energy.
They need to bind.
Yes.
So it's less. Otherwise, you escape, right? Very good. The same is going to happen here. We're going to have a mass, which will be the sum, and then some binding energy. This binding is going to be part of our observable. So the binding of the neutron star is very important. That makes this M a parameter that we need to match. If this was a black hole in GR, who is the M? Sorry? The same as the neutron star. Good. You can keep the mic by him. He likes to talk. Come closer.
Okay.
It's also a parameter, yeah?
Yes.
And very suggestive.
If the outside is vacuum, and if it's not rotating, we can use the Birkhoff theorem. So it's
We can use the Birkhoff theorem, yes, but we don't need the Birkhoff theorem if we have the solution. The Birkhoff theorem tells you that the solution will be determined by one parameter, which tells us we have this one parameter.
Exactly.
This is good.
Okay.
Now, does this M have to agree with the M in the Schwarzschild solution?
If in the long range, yes.
The long range what? Where is long range here?
No,
What do I do?
okay.
It's a good question, right? So what do we do in the case of any experiment? You have a prediction in the full theory, and you have a prediction in your effective theory. You compare. You go in the regime of overlap of validity, which you were saying correctly, far away. You compute something, and you compare. It's very useful to compare something physical, say a cross-section. You compute effective theory, a cross-section, you compute in the full theory, and then you know the coefficients in terms, say, of the mass of the W. You don't have to do it that way, because the full theory is the full theory. You can solve any parameter of the full theory that you want. For example, the potential. You can go from here and compute the perturbation, the 1 plus 2 phi, which comes from here. Now, notice something. This theory is localized on a source. So let's make it at rest. Let's make it, it's not moving, because I don't have to move it if I don't need to, right? So it's localized somewhere in space and time, but the integral in time will kill the dt, right? So it's somewhere with some charge, which is the mass. So the potential for this source obeys the Coulomb equation with a delta source localized here. So the potential will be proportional to delta, which will give us, right, the decay. Well, if you put, I have to put the GR par. If I put the GR par, I put an action for the GR par, right, that will give me the box par here. That will give me the G Newton par, right? So it will give me that the phi will go like Gm over R. The G will come from the bulk part of the Green's function of the theory. This comes from the source, right? And then I go far away to the H00 of Schwarzschild. I look very, very far away, so there are issues with coordinates and so on, but I'm going to just look in the limit at which I get into the Newtonian limit. And then I compare, and then I say, aha, that's the same M that appears here, so that's the same M. I can do the same with the spin, and if I'm not mistaken, that's exactly what Roy Kerr did to match the spin. That the parameter that he had in his solution was a spin. He looked far away, what a rotation would be far away, and he said, ah, that's the spin. But notice I do this as a matching calculation. Because the solution, what is the equation that this guy solved? I just told you, right? And not only outside, also inside. R mu nu, if this was a black hole, R mu nu would also be 0 here, everywhere. So notice that the equations don't match into each other at all. This theory is very different than this theory. In fact, this theory is very problematic. This theory has full nonlinear solutions, Schwarzschild. This theory will have a lot of trouble with the nonlinearities because you have to iterate the deltas at the same point. So this theory is going to blow up because of the point-particle approximation. And that's why it's an effective theory. That's why it's not ending. We need to keep going to absorb these terms. So the effective theory is not the same as the full theory. The full theory is very different. And in fact, if you believe that the string theory is the theory of everything, quantum field theory and string theory are not necessarily the same, not even close, right? So don't have to be the same theories, right? These ones have the same fields, but they don't even obey similar equations. And in fact, this theory is scaling invariant, whereas this theory is not. The solution, the way that M comes out is because of G. And where is G here? Do you see a G? I don't see any G. So we do a lot of cheating here. No, I'm far away from the singularity. No. I'm worried. I'm just saying that once you get close, this theory is not supposed to be valid at all scales. So they will never see the horizon directly, for example. You will see the horizon as a perturbative expansion. If you control all the nonlinearities and you take care of the fact that it blows up, when you do the calculation, you remove those. I'll tell you maybe how. Then this solution, as you keep going, will match this solution to all orders. But it will not be the same theory. Right? It's not the same theory. In fact, this theory is not that theory. Now, I was just saying something which is very cool. This has no scales. And all of the sudden, this has a scale. This one is there, it's sitting there in the matching. Right? How do we manufacture this scale? Well, because we cannot cheat by saying there is long, kind of, right? I mean, there are the nonlinearities, obviously, right? And there is short. And this, we say, well, now it's our guy. Because we look at the metric and say, we look far away, we're going to say our metric field will be some short scale UV here, G mu nu short, UV. And long, this is inside, and long outside. We integrate out the short scales of our metric, and because it's a fully nonlinear theory, we came out with a source for the long guys. The long guys are sourced by the short guys, and they look like this, far away, even though it's full vacuum. Obviously, if there is a T mu nu, if it's a neutron star, then obviously that goes into the T mu nu. But vacuum is the funny one.
So may I ask a dumb question? Because
you did already. Now you say, may I? Come on.
Okay, yeah. Another dumb question. So you say this this equation is
this one has no scale.
Exactly, but what do you mean by no scale? Because
do you see a scale?
Exactly. Okay, right there, no. But take for instance the Schwarzschild equation.
Yeah, but that's an integration constant. When you go solve the equation, you have a length because they are radius. So you have Rs over R. You don't know what this is. Yeah. That's the guy that becomes GM. Actually, I'm saying M, but M never comes along. It always gets with G. So that's why it's M, but it's actually GM what you really care. Yeah. Right? Okay. It's just because length potential
Yeah.
that I had the G that I manufactured myself when I did this.
Yeah.
When I did H over M Planck, I put G in there, and that's what the M came out here. But in reality, it's GM length that comes out of the solution as an integration constant. That's how you break the symmetry. But the solution, the equations don't have.
Equation don't. Yeah.
They don't have G.
I agree. I agree. Yeah.
This one does. It's right here.
Yes.
See? Okay, so if there's a T mu nu, you match the same observable, but then it will be an integral of that T mu nu over the surface that will give us this mass. Because that, in that case, the field far away will depend mostly at leading order in the 0, 0 component. Okay? So this is just fancy something that we all know. There's a theory of an object that I treat in an approximation, and the parameters of that theory I need to extract from some matching, which is the full theory calculation. We do this all the time, and this is the ideas of effective field theory. The UV becomes just parameters. When you solve for that scale, it sometimes goes by the name of decoupling, all the physics at longer scales is determined by the light fields, and all the heavy fields go into coefficients. Heavy, I mean, in this case, I'm talking about length. Now, notice something which is non-trivial, that nobody has asked, but it's kind of implicit, is that when I did this, I'm talking about length. I did not mention time. There is no decoupling in time. There is no decoupling in time for several reasons. First, there is no decoupling in time because the black holes absorb, and time scale of absorption could be very long. So you have to be very careful, and I haven't written yet the terms that will take care of that. And second, because when we look at the binary, there's a separation in scale in space, because R is literally shorter than lambda, but the time scale of lambda and the time scale of the period is exactly the same. In all cases, what that means is that the couplings of this theory, whatever they are, they will be time dependent. I cannot integrate out that time. I can in certain cases, but not always. And that's okay, because that variation in time is what's going to give me the fluxes and the waveforms that I want. That's a little bit different than standard QFTs when I have Lorentz invariance. Here, I break it explicitly. I recover it indirectly. And in scattering, we're not going to do that. And therefore, we're not going to have that problem. I mean, if we ignore absorption, absorption is another story. Okay? So now I have 15 more minutes, right, Ricardo? So, sorry? Okay. Let me just complete this so we see what theory we're dealing with. And then I'll tell you a little bit about how it works in the binary case. I want to give you the flavor of what's been, I mean, most of these ideas were originally put forward by Ira Rothstein and Walter Goldberger, and this is already something that goes back to 2003, and I did all the spin that I told you in 2005, so it's 20 years ago. And we have done a lot of calculations, Ricardo included. So I want to first give you the flavor of a modern, not so modern, before we go into the actual modern. Because it also sets the stage for what is different. If you have never seen the other way, you don't understand what is the leap to the scattering case. And I don't dare to tell you how these calculations were done in the past, because we are solving GR equations, right? And that's obviously a non-trivial task. That these tools are very nice because they literally separate what is relevant. When you talk about post-Newtonian, you end up with some power of V or some effect, and that you don't even know where it came from. Which ratio of which scales was the one that you were taking into account? Was it R over R, which is the V square? Was it R over lambda, which is order V? I didn't write that. order B. Because this is essentially like the frequency is the period, and that goes with the velocity. So you don't know where the things came from. And because GR is nonlinear, these scales talk to these scales, to the other scales. It's a mess. So knowing the theory doesn't mean that it's easy to solve. So how do we keep going? So we learned then that we're going to have some word length, and that's going to be some parameter. Let's call it tau for now, it doesn't matter. And then we roll, if we have two of these guys, we wrote this thing. And then it's not the end of the story. That was our first parameter. So the whole point is that we want this action to be a function of x and the e's, and then some coefficients, like the mass, that capture all the scale r. All the scale r is going to enter inside these parameters to some power. So there will be a derivative expansion of the metric field. The long fields are the metric. And this derivative will come with coefficients which have the scale r. And therefore, the C coefficients will be what, after matching, determine the new physics, the UV physics, and then there will be higher derivative terms that when you do an observable, they will scale with the parameter r. So they will have r over r, and that will be gm over r, and that will be the v squared, and so on and so forth. So in a derivative expansion of the long fields, the metric long, because all the short and the T mu nu and everything was inside here, what else can I write? Well, I can write the spin that I'm not writing. Let me just write it. But so there is some coupling to the so-called spin connection. MA minus. And this also has A. Oh, I call it AB here. It's called I. So there are different particles in principle. And this is the spin connection, the EDE of the flat, of the free-falling local frame that I had over here. I'm not going to waste much time on the spin, but this kind of looks like a dipole, right? Because this has first derivatives of the metric, but it's the spin. There's nothing else. Well, that we can think of. So that's the two light fields, the mass and the spin. Those guys, I mean, they do scale with R if you want, because GM is the scale and so on. But they are not yet sensitive. They are the lights, they are the collective motion, right? The Goldstone modes. They are the light fields in the sense that you move as a whole and you rotate as a whole. So you're not sensitive to size yet, right? There's not really the short scales. And then dot, 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 that means zero derivative, one derivative, then two derivatives. And that, here comes the P dot E. If I was looking into electromagnetism, it's the QE of gravity. And here there's also sign conventions. Depends. Sometimes you'll see it. EIJ. And this is defined again, like the spin, these AB indices. Let's call it AB then. They are defined in the local frame, and only the Q AB. Only the spatial part. These E's are also orthogonal to the velocity. So that's why I wrote IJ, because it becomes spatial at the end. But all these objects are defined in the local frame in which you have, say, a quadrupole mode. The same way that the spin in the local frame is what you expect. It's a rotation, an actual rotation of the Lorentz group. Of course, you can then define a spin with respect to the frame, the post-Newtonian frame, and they are not necessarily the same, and that causes a lot of trouble because sometimes you see answers in an object which is not the object that you naturally will associate with rotations. It doesn't matter. That's one of the most amazing things about physics as a whole, by nature, right? Is that it allows you to write the things in a way that is convenient, but it gives you all this freedom in which you might get confused about which parameters you're using to describe what, but the observable at the end doesn't matter, right? But you get all this freedom, which is convenient, right? It makes things easier. It allows you to write things in a nice, compact way with symmetries, diffeomorphisms, and so on. But then you have all this coordinate freedom. Well, similar with this guy. You can also think about internal symmetries in that case. There are frames which are natural, like coordinates which are natural, and the same with this, right? And this E is the Weil tensor. It's just some I don't have to use the Weil tensor, but what it means is because these guys are 0, all the traces are 0, I take them away from the Riemann tensor, because essentially they are 0 everywhere except on the point. But on the point, in my effective theory, those guys are infinite. So it's just like a pure counter term that I can just remove. In technical terms, there are ways to redefine your fields, which is what I was talking about, freedom. The metric itself is not necessarily observable. And you can change your metric fields to reabsorb and get rid of those terms. And this Q now, as I was saying, could depend on time. Well, this depends. And I have the interval tau. This object could, every particle can have one, right? What matters here is that this is like the Riemann tensor, which if I'm in the frame, the local frame on the ij indices, it's just this guy. Otherwise, it will be contracted with the velocities. And this second derivative of the metric, which is what I care about. This essentially is what gives me this type of coupling, which then makes the derivatives here that in the one-point function give me what you know in GR is this coupling. And that's this in the effective theory. So if you're in the one-point function, you look at the metric far away, and you say, what is this guy? For example, if you're looking at the binary as a whole, and you look far away, and you treat it as a point particle, if this was the whole binary as a quadrupole of the whole binary, and you look at the one-point function from this term, this goes like this, and then you get that the hij goes like this. You do dt, where is this? This is not supposed to go. Then you do this in some gauge, say tt gauge, square, and that gives you E dot, and that's exactly where it comes from here. So this theory pretty much gives you the quadrupole formula, right? For the binary, now I'm talking about every particle individually. Later, I'm going to put the binary as a point particle. It's going to have a total angular momentum, it's going to have a binding energy, and it's going to have a quadrupole moment. And it's going to have this quadrupole formula. You see how compact this is, right? This captures everything. And dot, dot, dot. In principle, you keep going. Higher derivatives, there are derivatives of these guys. There are octopoles and 16 poles and whatnot. Now, this guy that can depend on time, because we don't have the coupling necessarily in time, because absorption could operate on long time scales, will describe both dissipative effects and also conservative effects. So it will take care of absorption. How does it take care of absorption? Well, it takes care of absorption because this is a theory of time-dependent objects that will have, for example, let's go to the ij, jk, t prime, some Green's functions that will give you some response functions that could have imaginary parts, and those imaginary parts will give you absorption. So that time dependence in the one particle sector of these Green's functions width will give me absorption. There will be a conservative part. Why? Because there is also a response of the real part that we have like these guys. And exactly the same as in electromagnetism, the imaginary part of these guys is the absorption, the same way as those guys. And these are the Green's function of the response. That's literally the same. P response E imaginary part in the case in which these vectors are the same, but they don't have to be collinear. Will give me absorption, same there. The real part will give me the deformation, will give me the love number. So there will be a real part, which will be the conservative part, which is the real part of that response function. That will tell me that the Qij, in the limit in which the guys are spherically symmetric in isolation, it will be proportional to some object times the perturber, which is this guy, proportional to the external field. And this one, because it's conservative, I can plug it back, which means I can keep this for the absorption when I don't look at the real part, and the real part, what it's going to do is going to give me the E squared term in the action. And it will be some coefficient here. Sometimes it's called CE, which is like the love number. And this is a coefficient that has that many derivatives that will enter here at very high order. The absorption, though, is much more interesting because the whole function, this is a number, this is a function. For black holes, at the end, everything turns out to be just a number. It's gm to some power and so on, right? But if you have a neutron star, this is the whole function of frequency, if you go to frequency space, and we don't know it. So it could be very interesting to understand the absorption properties of neutron star. It enters for non-spinning at 4 post-Newtonian order, but 2.5 for spin. There's an enhancement because of superradiance for the black hole spinning case. We don't know if the neutron star will feature superradiance or not. So this is a very open question. There's a lot of now interest in understanding these absorptive properties. There's a lot of interest in understanding this guy in the effective theory because this is the love number that knows about the internal structure, that knows about where the black holes. This is 0 for black holes in 4 dimensions Einstein gravity. It's not 0 for anything else. Even higher dimension black holes in Einstein gravity are not 0. There's something very special about 4 dimensions, that there's a lot of symmetries about the solutions of the perturbation, which will be, this is a 2 point, this is a, if you look at the 1 point function as I was doing with these things, all of this guy, this is Birkhoff's theorem. There are only 2 Goldstone modes, the spin and the mass, right? Then you have the 1 point function if you're binary, which you're radiating, and then you have 2 point functions, which are not unique. Now it's not Birkhoff anymore. There's a response. Some goes into the perturbation, and then 1 point function. So that is a perturbed solution, right? And this, when you study the perturbations in the equations, like Tukowski equations or whatever you solve, you can understand when you match the full theory calculation to the effective theory. The effective theory will have just this diagram. The full theory will have some metric perturbation that you put some boundary conditions at infinity because you have some external field. And that solution have to match, and then you can read off this thing. And properties of that solution in GR, in Schwarzschild backgrounds and Kerr backgrounds, kind of explain, not directly, but indirectly why those guys are not there. There are some ladder symmetries that allow you to see why, how do you find solutions, why you don't see this. Ultimately, it's actually pretty simple. I can give you, I can do that later, or I can give a one-line answer why this is 0 in GR. It's very peculiar of GR in 4 dimensions. There's a lot of fancy words, but it all boils down to something very simple. I mean, it's not the no-Hertz theorem, because the no-Hertz theorem also applies in higher dimensions, and yet you have love numbers. So in 4 dimensions, they overlap. And I show you why they overlap. Or a very quick proof that, that it's not a real proof, but it's an idea of why. That is not true. It doesn't hold in higher dimensions. Because the love number is not 0, and you still have the Noether theorem, spherically symmetric, right? You have black rings and whatnot. With the mass and the spin of the black holes, whereas you do have low numbers in high dimensions. The reason why in 4 they kind of overlap, I mean, this is not the Noether theorem. The Noether theorem says boundary conditions are flat. This is not the same, and that's why love in high dimensions exists, even though if you have high dimensions flat, you don't get, unless you chop topology, right? You don't get other than mass and spin. But in 4 dimensions, something very funny happens. These two things decouple. The perturbation. So if you E square, one goes into the background, one goes into the perturbation. In GR, you have the solution that you try to solve, right? So here you compute the H induced by this. That would be this diagram, right? In GR, in 4 dimensions, these two lines decouple. There is something called the Weyl decomposition that is linear. It's a Laplacian, cylindrical Laplacian of some u in the 0, 0 component, the e to the u, and there's a v as well. 0 in those cylindrical coordinates, which is linear, which means that if you have a perturbation, you just sum them. They add up. And because now the Noether theorem tells you that you cannot have regular solutions on the horizon, you cannot inherit that in this calculation. And that basically means that you will not have a love number, which is the growing mode, and at the same time a decay mode, which is regular at the horizon. The regular solutions at the horizon don't have decay modes at infinity and vice versa. And it's literally because those two things decouple. So you can really track what you did before for the Noether theorem, you do it now as well. And there is kind of a proof in this direction by, I forgot the name actually. There's a paper that kind of goes in this direction. It does it in a fancy way. There is this so-called Geroch multiple moments, and he shows that the Geroch multiple moments are 0. But it boils down to this. This Weyl decomposition does not exist. It exists in phi, and it's called the rod decomposition. There is more than one guy. And in 6, it doesn't exist anymore. You cannot decouple the equations anymore. And lo and behold, you get love numbers. So I think there is some symmetry arguments, but those symmetries are basically telling you that there is a very special decomposition in 4 dimensions. Very good. So then we have our theory. This now absorption or a permanent guy. For example, if you have a QIJ that in the background of the short of the UV physics is not 0, if the object is not a response, the response part got the grid functions and the E part, that is already taken care of. But if you have on the short something proportional to an object, for example, SI, Fj, Kk, spin square, that's how this enters. So the spin square coupling will also enter here. There's a quadrupole of a spinning black hole, and it will couple here to some coefficient that is 1/2m in GR, but it could be something else in another theory. It will also be captured by this effective theory. This effective theory captures now everything. It captures a single object that has some absorptive properties, some love numbers, some rotation, some angular momentum, some binding energy. It captures also the two-body problem, which has some total binding energy, some angular momentum, some quadrupole moment that radiates, as we saw. And of course, it can have external love numbers, but those effects are very high if we put that guy in an external field. In terms of absorption and so on, that's all taken into account because we control exactly this theory. We know exactly who the theory is, the theory of the two-point particle. Of course, there will be absorption at the very end, also in the binary case, from the black holes themselves, but not ultimately in this theory. There will be dissipation in this theory. You have to tell me how you're going to treat the fact that your radiation reacts on the system, which is non-trivial. I won't tell you much about that, but you can ask me. and dot, 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 because in principle, I mean, they are all the higher order effects. So now what is the name of the game?
So can I ask a question here?
Ah.
Yeah. So I'd like to know, okay, so it's not clear, it was not quite clear for me how this quadrupole moment relates to the quadrupole moments of the stationary object.
Of the what?
Of the stationary object. So you have two different objects, right? Which far away of each other, they have their own multiple moments, right?
Yeah, they could have, for example, if they rotate differently, they have different spin-induced quadrupoles. If it's a star that has a permanent quadrupole, then each will have a different one. Then I have a binary which has the common quadrupole of the system. I'm not sure what I'm referring to.
Yeah, so this quadrupole moment that you're showing is englobing all of these quadrupole contributions from the quadrupole moments from the separate objects and as well from the dynamics of the inspired object, right?
I don't understand the question.
Okay, I can send you a message later. Thank you.
No, it's fine. I just acoustically did not understand the question, but this is my limitation, not your problem.
This is Ricardo speaking. So this quadruple Rafael is talking about is the quadruple of the single object now?
Of the single object, yes. Is that what you're talking about? This is a single object, and remember later, when we treat the binary as a single object, then the two bodies will combine into an object that I'm going to call Q. But it's always a one particle system. If you worry about the sum over A, then I'm going to have just one binary at the end, and when I have one binary, I only have one. Is that what you're asking?
Etevaldo, are you fine?
Yes, so how this quadrupole moment of this Q that you're writing can be written in terms of these two different objects, of the quadrupole moments of the separate objects.
Ah, later you mean? Later in the binary. Ah, okay, no, I haven't told you that yet. That's the matching that I was referring. I have to do something similar to what we did here. That's what I was going to do next. I'm going to explain to you who these guys are. For example, if you compute the one-point function in care, and you see that there is a component that goes like the spin square in the metric, the same way that you did this, you can fit this coefficient for the one-point function of the care black hole and my effective theory, and it will tell you this goes like S squared. And the coefficient is 1 over 2m because that's the quadruple of the Kerr solution. That's one way to do it. You compute the metric. For the response functions, I was explaining here, the operator here in the effective theory is trivial, it's just this. You put 1 on the background of an external field, and you compute the perturbation, and you match in GR the perturbations of a black hole in which far away you get some non-zero background, external field. And then you match. In the derivative expansion, this is the first guy to show up. So you have a 1 over r expansion in your metric, and then you compare the 1 over r's. And then here there's a quadruple that goes like 1 over r to the fifth, say, xx. And that responds, and that's the part that you want. And then there's some growing mode, which is the external part, that's your background. This is how these calculations are done. Love number, you solve in the full GR calculation the perturbation, and you match into the effective theory. You could also do this on shell. This is a 2-point function, so you can do scattering. You send something in, something goes out, you compute a cross-section here, and here it's very easy because there are 4 derivatives in the amplitude square, so you get 8 derivatives. So in the effective theory, you get something like 8 to the A, R Schwarzschild. Cross-section is area, so it has nothing to do other than 10. And then you compute in the effective theory, you do the approximation. Well, R Schwarzschild here doesn't exist, right? It's GM. I just replace it by Schwarzschild because in the effective theory, there is no horizon. There is only G from the M Planck, from the bulk, and there is M from the M here. So what you get here is not R Schwarzschild, but ultimately it will be R Schwarzschild is truly in the full theory. You're calculating the full theory in this limit, and you match. You look at something that scales like omega 2. In here, there is no R Schwarzschild, right? So here you're going to have the CE coefficient square and G. I was just M-Planck square, so G upstairs. So this is the effective theory. There is no R Schwarzschild, but that's the only thing that can depend on the CEs. That would be the effective theory. That's this operator, right? And in the full theory, there is R Schwarzschild, so you go to a small frequency, and then you get the 10 if you want. And then you compare and say, aha, then I know what this coefficient has to be, and then the CE coefficient will have to go as R Schwarzschild over M Planck, which is the R to the fifth that I was saying before. The difference is that in Schwarzschild, the length and the mass are comparable, so it should have been R to the 4, but because the length is comparable to the mass, then there's a 1 over G, that was the GM, so it's M length to the 4, but then becomes R to the 5th. And then you know what this coefficient is by comparing those two things. And that's the number that you're going to have here will tell you what is this. This happens to be 0 in D equal 4, which is what we've been discussing. But in other dimensions, or for a neutron star, it will not be R Schwarzschild, it will be the scales of the size of the star. You will do the matching. So that's how we do it. We do a calculation in the full theory. The effective theory doesn't have the UV scale, R Schwarzschild, but I was just doing the unit thing. It has to scale with that, so the only thing you're looking for is this dimensionless number that will appear here, like the 1,000 for the neutron star thing. But depends on the equation state, of course, right? It will be a dimensionless number depending on the equation state. Now you might ask, what happens in the binary case? I can do the same. I can study, for example, what is the field far away. But another way to do it will be to match the T mu nu of the system and realize that there is a connection between the multiple moments, all of them, and moments of the T mu nu. I'll show you maybe tomorrow in the first 10 minutes how this works. And if I can relate the moments of T mu nu to these guys, I know what the T mu nu is, and these guys will have the T mu nu of the system, for example, a leading order if I had the T00, say, and this becomes a leading order just this. Then this will have a sum over the MD taus, which will have a delta of x minus x1 plus delta of x minus x2. And then here, you're going to have, you hit the 1, 1, or you hit the 2, 2, so you're going to have a sum over the particles, and then you get the usual thing of the sum of xx. And that's how you know what this is as a function of the parameters of now UUV, because these are the inside guys, and my effective theory is a Q, and this effective theory, the UV, is the X. And that's how you match. So match effective theory, full theory, compare in the limit of validity. I can do the same here. Compare, I haven't told you why this is this, but I can show you next time. And then you compare in the full theory. And I know the full theory now because the full theory is these two binaries. It's two of these guys with two deltas, and I do the calculation. Now I can actually do it and tell you who this matching coefficient is. It's not the end of the story because the T00 will also have binding that will couple to the H00, sorry, that couples to the 00, and so this type of diagrams also contribute here. You do all of this, you get the Qs, and remember that I square the one-point function, I get fluxes. So if I just square the one-point function with the Qs that I get out of the matching, I can literally compute the waveforms. Precisely doing this, and this is how we do it. Through this matching, in this case, we know exactly what the two-body system full theory is. In the other case, we don't. We do the matching with the Kerr or the Schwarzschild solution. I mean, we know in Kerr and Schwarzschild, but in general, we don't know with objects who have this CE, and then we get it from observations. This CE will enter in the waveform because the effective theory tells us exactly how it enters. It becomes a number. This is the beauty of the effective theory. I don't know anything about the UV scales, but I know how the long scale behaves. I know it will be just a number or a function because there is no decoupling in time. It decouples in space, but not in time. So there will be an unknown function of time or frequency for the case of absorption, but for the most part, it's things that I can parameterize when I don't know. When I know, I do the matching. Is that more or less clear?
Yes, yes. Thank you very much.
Thanks. I'll show you how, this was very quick, but I'll show you next time how this works. But that's the name of the game. Iterate this theory, and that's it. Compute who these Qs are for the binary, and these Qs will depend on the x's, and the x's, when I take derivatives, they will depend on the motion that I solved already in the previous theory when there were point particles interacting through forces. I haven't told you exactly how to do that, but you can see more or less where it's going. And that gives me the waveform. Then there is other types. So this decouples everything. This really seems to imply that when I deal with this, individually, and then I put it here, and it's the end of the story. I just compute the matching, and I do the square, and you're done. You're almost done. The problem is, which I'll discuss a little bit, is there are things called like tails, and that's when the scale R and the scale lambda start talking to each other. And that is very interesting, but it mixes. Now these Qs, the theory of the Qs, can start talking with the Qs themselves and with the M of the whole binary. And therefore, this very nice TT gauge thing that we're writing here is not the whole story, because that guy, oh, wait a second, can start talking with the mass. And then these guys get renormalized into sometimes called radiative multiples. And that makes the theory very interesting, because there are many of these guys. There are things that you can exponentiate, there are logarithmic running, and there is also memories, which we are now pretty much trying to understand, in which the radiation itself talks to the radiation. And that's when the theory becomes very interesting. When you start coupling the different modes. This comes out of the Qs, but in reality, it could also be radiating away from the binding, right? So that's the fun part of all of this. But the good thing is that it's systematic. I know how to treat all of this. I know what I need to calculate. I know what I need to construct this. And that's how this ultimately works. So this was Modern Approaches 101, which means modern as of 2003. Now, what we will do, I'll tell you at the beginning next time how this works, just to complete the idea. Now, next time we're going to do is that we are not going to, next time and the follow, is what is more, I mean, very few people are doing this right now. We are, obviously, but most of the groups that are interested in gravitational waves from the modern point of view are doing it from the scattering viewpoint, and that's why I want to talk to you about the scattering part, because even though this is probably more important in the sense that we are not yet in the scattering at the same level that we are here, but there is a lot of potential to like overcome some difficulties of this formalism and move even forward beyond what is possible here. There are some issues in this way of doing things, which in scattering are nicer, because here, for example, I'm telling you, I compute multiples, I compute equations of motion because I take derivatives, I compute binding energies, and compute evolutions in some potential. Blah. There are a lot of intermediate steps. It makes your life easier because you can go really high this way, but there are a lot of intermediate steps of choices that you can make that can confuse you. Intermediate divergences, for example, I told you that this blows up, so you need to regularize it, and I didn't tell you, but these operators are there also to absorb the divergences. And then these guys could also have divergences, and some of these divergences are associated with the fact that I split the field into the R and the lambda scale. So sometimes the R scale, it starts interfering with the lambda scale, and therefore it produces overlappings and divergences. It's very useful to calculate, but it has a lot of subtleties. If I don't do that, which is what the scattering does, I'm not going to separate this guy from this guy anymore. Then all those subtleties are gone. I'm going to compute observables. I don't care about gauges. I don't care about proper times at the position of the particles, at some nothing. I just send something in Minkowski, and I collect something out, like an angle, and it kind of get cleaner than this. And I'm not going to separate anymore, at least not originally. I will see that we will ultimately do it, but at a different level, the R and the lambda scale. I don't separate them anymore. Everything goes. I sum everything. Everything that contribute, everything goes. And I compute this with all the effects in it. The angle with all the forces that bind the system and all the radiation that comes back and reacts in the system and goes to infinity. Everything is included. Of course, that makes the calculations way more challenging, including everything at once, because now I'm going to talk maybe to a little bit more, and I'm wrapping up, to the people who understand what I'm saying, but if you do a calculation in which you have, say, something like this, which is like, say, a three-loop diagram with some sources interacted to some gravitational field. This is not necessarily saying anything about which propagators I'm using. This is some 1/p² propagator on a three-loop diagram, so you get a three-loop relativistic integral. It's very hard. How does effective theory, how this theory does this? Well, there are different regions of this integral. And this split is basically taking into account those regions. There's some that bind and some that radiate. Some of these propagators are off-shell, some of those propagators are on-shell. Part of this could be, oh, this is binding. This guy here could be, oh, it's the radiation that is back reacting in the system. So this could be binding, this could be radiation, and the radiation could be talking to the binding of the system. All of this in the theory that we have, we compute this into the Qs. We match now into a QQ talking to the potential. This integral is way, way, way easier than calculating this integral. All I did is a one-step matching and then a two-loop of a three-loop calculation. How did I do that? Instead of doing directly in the diagram, I did it through all these steps. Because I can do this matching with the fields and then do the calculation directly in the fields, in the effective theory. Without having to match the diagram, I know how to do that calculation at the level of the fields. That's what the effective theories do. The effective theories takes a full calculation and finds the different regions of relevance of the theory, construct the effective theory that matches into the regime of validity of that full calculation. And this is way easier to do than this calculation. But if I now know how to do this calculation, forget about this. And that's why we go here. Of course, here we can do way more than here. Here we can do 4, 5 in this calculation of Pn, not here yet. And that's why we don't do the same yet. But ultimately, we'll see how. And there are other problems between going from here to the bound case, which I'll tell you that have to do with these tails. But in essence, how this modern approach works, what is it that you're doing? It's essentially reducing a very complicated problem into pieces, taking advantage of the relevant scales in the problem. Which if you're strong enough to solve the whole problem, good for you. But if you're not, if you're smart, you can split it. Ultimately, you will realize that this split will reappear in the full problem, but in a different flavor. It will be through boundary conditions. It will be, I know how to solve the full integral up to some constants. How do I get those constants? Well, I'm going to match into this theory where I know how to do it. And then the full theory solution, the full theory now, up to constants that I know from the EFT of the Pn. And that's going to be the name of the game. Yeah? And I should stop here. Huh? OK, thank you very much.
You're not over time, just that.
Ah, OK. No, since you stood up, I'm not sure if you were kicking me out or what.
There might, I'm not sure, but there might be coffee upstairs.
Ah.
So, if you have a microphone, right, to share?
Please ask. I mean, it's just a few lectures. Obviously, if it was a school, I could target a specific calculation and work on some, but I think the best part is to see a flavor and ring ideas that ultimately later, when you approach a problem, you can associate these ideas to whatever it is that you're interested in. I don't expect you to understand everything, obviously, but it's very nice, at least for me, when I started learning all these things as well, right? To recast the knowledge that you think you have in a way which is very clear and systematic of what is it ultimately that we're doing, right? that you're doing it without stopping and thinking, oh, that's what I'm doing. And then once you realize that that's a tool, I can use it here too. And that's how this proliferates. Right?
There's no coffee upstairs. No,
that was a bad thing to do. Announce something that is not. You go check, then come back and say nothing.
No, just a comment about what you said at the beginning about the data analysis. No, it's very important to have a theory prediction because when you try to fit your waveform model to the data, there is lots of degeneracies between astrophysical parameters and fundamental physics parameters. So unless you have a clean prediction from the fundamental physics, if you start having some uncertainty in the fundamental physics, then you go in fit, and you never know if you are biasing the astrophysical parameter or if you are uncertain of the fundamental physics. So you fix the fundamental physics first, and then you go and do as much astrophysics as you can.
We have a bias there too, right? I like GR. Somebody can say, okay, we have to free that as well. And then, okay.
No,
then
my students know that I don't go beyond GR.
Okay,
so.
good. Because you could even question the starting point, right? Because at some point you have to stop. Let's believe in the theory and use it to learn about the source, right? Nobody looks at the stars and say, you know what? I'm going to put a mass on the photon. No, right? They'll say, I'm going to learn about supernovae, right? I'm going to learn about astrophysics. Nobody's going to question Maxwell by looking at the propagation of light. Of course, we can question GR, but we question GR because it's closer in time. If it was 500 years of GR, everybody would be like Maxwell, right? It's the freaking graviton. We're done. Let's move on, right? But, of course, there's the cosmological constant, which is not there in QED. QED is close, very nice, pretty. There is no hierarchy problem in QED if you think about QED by itself, right? There's a lot of hierarchy problems in gravity, and therefore, maybe there is a mass of the gravity. But then you have to explain to me why it's so small. Okay, it's technically natural, but it's very unnaturally small, right? Which is also...
The source modeling, we are at the scale of the kilometer, hundreds of kilometers. So, I mean, the eventual infrared modification of gravity are very far from the source modeling.
No, if you think about curvature correction, exactly. If you think about curvature corrections, what Ricardo is saying, if you add an R squared to the bulk, and you put here something, right? Well, it depends, it's dimensionless, right? But if you pull out the GM, right? So there is something that most likely will be L Planck suppressed. In quantum, in one loop gravity, for example, it's L Planck. But if you put something else, it will be a length scale. Why would this be 10 kilometers, right? And why we haven't seen it? You have to shield this from everything else, right? But of course, there are ways to do it. It's not impossible. It's just very contrived, ultimately. There are fun, okay, there are uninteresting ways to do it, and there are interesting ways to do it. And the interesting way to do it, I mean, they are interesting for a reason, led to a lot of these Galilean symmetries and whatnot, which are very interesting, which ultimately have to do with coupling all these extra light states, right? Because in principle, once something that is obvious, right, but we don't say, I mean, if you are higher derivative things, that means that if you look at the propagator of as a full theory thing, now you have higher P's, you have more poles, you have more modes. The things that those are heavy, so you integrate them out and you don't care. But if you keep that as a full theory, then you're fucked because now you have to deal with that. As an effective theory, all good. But if that you're going to claim is the full theory, then you have a problem. The same problem that we have with this, right? Not exactly the same, but I'm saying if you claim that this is your full theory, this GR, R mu nu, equal delta, doesn't exist. You just cannot construct that theory. It's divergent, not even as a distribution. You iterate the deltas and you end up with delta, it's gone. As an effective theory, it's completely fine. Because I don't stop at R. I keep adding stuff that fixes it, and there's some UV physics that takes care of it. But if you claim that's the full theory, there are new degrees of freedom. And that's obvious because the R squared inflation is the same as a scalar field because you have a new mode. So that you didn't invent anything new, right? If it's your full theory, fine. But why terminate there, right? I don't know. At the same time, I mean, I don't know about massive gravity. I mean, that's very, let me put it this way. There's originally, the whole massive gravity story was very interesting because it was a very sensible question. Can we have a Higgs mechanism for gravity? And it's not obvious how to make it work, right? So when Jan Mills started playing with modifications of gauge theories, I mean, they had the neutron and the proton, right? So the isospin had nothing to do with nature, but the idea was interesting and it took off. Maybe these ideas are interesting. The mechanism itself could be interesting. And there are many things that led to a lot of interesting theories. The point is that right now, like Ricardo said, I mean, we are biased because there is no observational evidence that we need to do anything with GR. So why touch, if it ain't broke, don't fix it, right? At least at this scale, okay, obviously, quantum gravity is another story, right? Of course, at this scale, I had no idea, right? Sure. I mean, I'm talking about this kind of things, right? Long-distance modifications of GR, which would be putting a mass to the graviton, by the way. That's a very long-distance modification.
Also, you don't prove a theory right. You just keep passing the test, but you never prove a theory right.
It's like the new generations just basically, they grow up with a new theory the same way that we grow up with Newtonian mechanics. We just don't question it, we just absorb it. It's just part of our knowledge, right? At some point, I mean, it just becomes, obviously, I mean, until an experiment disproves it, we cannot do anything, right? But people are questioning GR now based on aesthetics, right? They don't like aesthetics. They don't like lambda, right? I mean, they're fine. I mean, okay, let's not go there. But at some point, it's also a minimalistic aesthetic approach. If you're going to introduce a lot of garbage, I mean, sorry, I shouldn't say garbage.
Epicycles.
If you put a lot of extra stuff to fix a problem that is not even there, and then you have to fix the problems that you created, you make it very contrived, like by matrix and what, then, I mean, at some point you have to question what is it that you're gaining, right? But nature is ultimate. I mean, if somebody sits here and says, look, nature is like this, then okay, I do engineering, fine. But still, I mean, it's what it is, right? Nature is pretty and continues to amaze us, right? It would be unkind of nature to make it by gravity, massive gravity. So, but that doesn't, nature doesn't have to be kind to us, right? That's what.
Let's put it this way. After over 100 years, there's still a lot to learn about GR.
That's another story. Learning, this is what Nima will say. Don't modify it, understand it, right? And that's ultimately what we are trying to do. Because it's a beautiful theory that is teaching us a lot. This whole story of love numbers, for example, right? And Noether theorem is very interesting. I mean, things that Fabian will tell you about also if you study perturbations on a background, the properties of the solutions. This is a beautiful theory, right? Why modify it? Just freaking understand it, right?
Going once. Good.
So you mentioned different parameters entering at different orders.
Yes.
Right? So which one exactly enters at 5 p.m. related
That's
to
the love number. That's this
okay.
response. This CE square term. If you go ahead and compute at which order in the phase evolution the CE enters, is order V to the 10.
And can you see that easily?
I just show you.
10?
Is for example, if you, for a neutron star, there's an enhancement parameter, right? But if you just look at the scaling of CE, it goes like R Schwarzschild to the 5th over G. Just compute in the effective theory and the full theory, right? The dimensions of the operator, D, the E here has D square, and that's an amplitude, and then your cross-section is square. So you end up with something omega to the R Schwarzschild to the 10, and this is C square. So C square is R10, is R5. And now compute a phase is dimensionless. So you have no choice. Just on dimensional analysis, it has to be something like this. And this is V10, right?
Okay, thank you.
Rafael will be in room 112, right?
112.
112 on the first floor until Friday next week?
Yeah, I'm 2 weeks here, so
yeah.
Because we have the 2 week, so Thursday and then Tuesday, Thursday again, right?
So feel free to
Please
talk to him. But let me take the occasion to advertise Fabian's seminar tomorrow at 11.
And I have the colloquium tomorrow too, right?
Yeah, you have the colloquium at 2.
At 2 p.m.,
You have the colloquium. Fabian is giving a research seminar at 11 here.
Where he's going to talk about spin and some interesting things about doing some similar related perturbative calculation.
You're giving me a spoiler.
Well, I'm introducing, I'm giving a very brief introduction of motivational. No, I mean, certainly spin is by far one of the most interesting aspects here. But because it entails a lot of extra knowledge, spin in GR by itself, it will take me the 4 lectures just to talk about spin in GR. And therefore, we don't do anything like this. Right? Before I did spin in GR, people didn't even know how to compute spin-spin interactions. Right? So literally, it was a completely new territory. And we're talking about 2005. Okay? So there's a lot to learn about spin in GR.
Last chance? Okay.
I have one more. So the multiple moments that you wrote in this effective action, the multiple moments, the quadruple.
Qs?
Yeah, for instance.
Which Q? The binary Q or the one particle Q?
It could be, let's say, the binary Q.
The binary Q, yes.
It is trace-free, right?
When it couples to E, these guys are orthogonal to the velocity and trace-free, yes. So they're space-like and trace-free, because E is symmetric trace-free. It just happens automatically.
Okay, so do these traces of these multiple moments, do they enter also as couplings in the effective action?
No, they decouple, right? That's what I just told you. The E is symmetric trace-free. So the Q trace vanishes. In other words, okay, good question. In other words, if there was a trace, you had to couple to a scalar. So R, but R I can remove. So literally, it's not there. Because it will go into the trace of this guy.
Well, we might disagree on this, but we can.
You might disagree with me or with him?
With you.
Ah, okay.
But in the sense that you might have some coupling to the longitudinal modes of gravity with the trace of Q. It's not radiative, but the longitudinal mode is still there.
What, but you mean in GR?
Yes.
No, but this guy is gone. So even if I couple this guy to the whole R mu nu, there will be the traces. I can always write E plus traces, and the trace will couple to R. R and R mu nu, and those I can remove. They're gone.
No, I mean...
Imagine you did that. Imagine you couple this to full Riemann. And now I write this as Weil plus traces. Then the traces will couple to the R and R mu nu and so on. They're all gone. Field redefined away.
No, but I mean, they still give a curvature. I mean,
they still what?
The traces of the quadruple. I mean, okay, they still curve the space-time around the object.
The traces of the quadruple.
Yes, I mean, if you start from the fundamental, just a bunch of masses, and then you multiple expand, you have a trace of the quadruple that source some gravitational field. Some
well, depends. Okay,
field.
I'm not sure.
I know you wouldn't agree, but we can discuss later.
Okay, sure. Yeah.
So that formula you wrote for the quadruple moment.
This one, I'll tell you next time where it comes from.
I don't know if you're gonna also talk about this.
I will tell you where it came from. Yeah.
Okay, but that formula works for if you're in the scenario of 2-point particles.
No, this T is any T.
If we could
if it's a two-body, then I have two deltas, and I sum 1 plus 2. But if it was something else, I would just get this. Okay. This theory. Yeah. Sorry, good question. This theory that couples Q to E could couple a blob of matter.
Okay.
With some T mu nu that has a quadruple.
Yeah.
That doesn't necessarily have to be two particles.
But there, you're considering the particles, in between the particles, we have a Minkowski space. That's flat space.
No. This type of diagrams, two particles binding also contributes to this. But the T00 also gets corrections from this binding.
But if you're in curved space, that formula works?
This is curved space. This is curved space between the bodies.
Okay.
The two bodies get a 1/r potential. This is the H00 curve. And this produces an H mu nu that gives me a T mu nu that accounts for the curvature in between the guys. In other words, this T mu nu is like the pseudo-Landau tensor.
Okay. Oh, yeah. Okay. But for instance, if you have... sorry. If you have, for instance, that axion-like cloud of
but that's not the binary. That's a
around,
one guy.
Exactly. But if it's around,
Then I do
very close
something else.
to-
Then I do something else.
Okay.
Then I look far away at the solution,
Okay.
and then I just match. In the case of a perturbation, like we were discussing with the love number, just that piece, just what the love number is by looking at the perturbation. I don't need to know the whole Qij and so. I mean, there is a contribution from the spin.
Okay.
But if I don't care about the spin, because the spin is alpha for those guys, and that could be small, then I just care about the same love number calculation that people do for black holes, for all that thing.
So the idea is to do some kind of multiple expansion?
No, remember, if I just care about the number, because the object is spherically symmetric in isolation, I just look at the response.
Yeah.
This is not the response. This is the actual value on the short modes.
Intrinsic.
The intrinsic, exactly.
I know.
So in the axion-like particles, there is no, well, there is an intrinsic because it's spin. But if you ignore the spin, there is no intrinsic, it's the response. And so I do the matching of the response.
Okay.
In this case, I care about the intrinsic. The response will be put in the binary in a Sanofi, which I don't.
Okay.
I mean, I do, but I don't. I mean, you know what I mean. Does that answer the question? But it's a very good question about this T mu nu, about curvature, because this T mu nu that defines the Q is the full T mu nu, which is conserved. And maybe we can have an argument with Ricardo now. It's the full T mu nu, which is conserved, not the T mu nu of just the sources.
But that's flat space.
This derivative is flat, but this guy includes everything that goes on in here.
Okay.
In other words, this T mu nu includes all the h square, h cube, blah, 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 of the Landau pseudotensor.
Yeah, because naively I would put the Landau.
No, what I mean is something, if you're comfortable with diagrams, what I mean is something that the coupling T mu nu, h mu nu, then you have in the action higher h cube, blah, blah, blah. Right? The h square is the bulk, the square HH. Source, higher order. This is source. It's the honest T mu nu. Now this guy has h square h. Now these guys I'm going to call now short. I'm going to leave between the binary, and this one is going to radiate. This coupling now, this h square looks like this one. So then you become T mu nu plus h square h. So that's where h, I match this into my pseudo T mu nu.
Okay.
And that's the guy that enters here. Okay. A quick excursion by Nathan and then disappear again. I see. Thank you. Oh. This thing is very uncomfortable. Now my ears hurt.